miles. So this number gets reduced to somewhere around 20. So okay. Uh, yeah, and if you are having any technical issues, please feel free and let us know. Okay, so I'll wait for a minute, and if there are no other pressing questions, I just wanted to make sure everybody's getting uh, some new designs, analogs for the query compound. So if you're getting those results, please confirm that in chat. Okay, so I'm not getting any responses, or at least on the chat that I'm looking at, I don't see any responses here. Is my screen looking okay and my voice coming through? Hello? Okay. Awesome. So assuming that everybody's getting some designs from the previous step where we use the function to generate new designs, I will go ahead to the third section. So just to briefly capture what we have gone through so far, we have gone over functionalities that are provided with the pre-trained megamolbart model, and that those functionalities can be accessed using inference wrapper. And the main three functionalities are going from smiles to hiddens or smiles to embeddings, or from hidden state to smiles representation. We have looked at the examples to see how these functionalities work in real time for our queries. And then we have also looked at a function where we can generate new uh, small molecule designs. Okay, so let's now move to the third section, which is generating a prediction model using learned embeddings. So often you deal with a scenario where you have a data set of small molecule compounds and you would like to predict certain properties for those compounds. These compounds can be under investigation, meaning they are in early stage of drug discovery, and you would like to know whether those compounds are soluble or they are what their extent of lipophilicity or their molecular solubility, hydration free energy, other values like log P, log D. Or you may also want to predict certain behavior like its hERG inhibition potential or their blood-brain barrier permeability. So if you have a chemical data set and if you want to predict those properties, traditional way is to generate descriptors for each of those compounds. They could be Morgan fingerprints, for example. So chemical fingerprints capturing the chemical nature of the compound and then trying to fit a model for a model from the data set against a certain property. So here we'll do a similar exercise. We will uh, make a prediction model using Morgan fingerprints, and then we'll also make a prediction model using embeddings that we obtained from pre-trained megamolbart model. And then we'll compare how uh, uh, these two models perform. So there are several data sets available with certain physiochemical properties. For this example, we will be using a dataset that's curated by MoleculeNet, and we'll be using water solubility data. So you can go to this link to find out the datasets, find out more about the datasets. But here we'll be using water solubility data. The dataset is already copied in the local directory there where we are running this notebook. So there is no need to download a new dataset. We already have it. And what the dataset contains, it's about 1,129 observations or this many small molecule compounds and their ESOL property or log solubility in moles per liter values. Okay, so coming to those cells, let's execute the first cell. So and let's read it into a QDF data file. So here is just to show. Uh, so basically, this data set is not uh, super large in terms of its size, but if you have large data sets and you want to leverage the GPU acceleration, you can use the QDF or CUDA accelerated data frame libraries that are available through Rapids. Rapids is an open source sort of a platform or open source collection of libraries, uh, initially developed by NVIDIA researchers, but later on now it's open source and it's a community-driven effort. So for pandas, you have analogous QDF data frame. For uh, scikit-learn libraries, you have analogous CUDA accelerated versions, QML, also available through Rapids. So for this particular data frame, we are looking at its shape, and we have 1,128 compounds, and we have 4 columns. Okay, for all these compounds, let's obtain embeddings. So embedding meaning we are uh, passing through the compounds through encoder and obtaining embeddings from the learned latent space representation, right? So we are calling again the same function that we used before, smiles to embedding, using our inference wrapper connection. And we have, for every compound in the data set, we are obtaining embeddings. So we are doing this operation in chunks of 100 compounds in a while loop. So as you can see, the embedding calculation was pretty fast. It took less than a second to go through the whole 1,128 compounds and obtain embeddings for them. Okay, let's look at the data frame and what it looks like. So far in our example data frame, we have smiles in one column, we have embeddings, and we have Y column. So Y is basically this is a target prediction column. So Y here represents ESOL value, also mentioned in this comment here. So we are basically reading the Y value as ESOL value here. And for the embedding, so we have 512 length vector for every compound as embedding. Similarly, let's use RDKit functionality, get Morgan fingerprint as bit vector. Here we are also specifying the radius, so meaning how detailed you want to examine all the chemical features or all the atoms in a compound. So we are basically specifying radius of 3 and the fingerprint vector length of 1024, meaning we want to capture 1024 different features, whether they are present or not, and we want to evaluate 3 molecules, up to 3 molecules connected to the molecule that we are investigating. So uh, again, this for loop does the same thing, basically going through every compound, generating a Morgan fingerprint as a bit vector, and saving in a data frame. So let's execute this cell. And again, it took less than a second to obtain fingerprint. And that fingerprint column contains all those fingerprints that are calculated. So for example, you'll see a vector of length 1024, and at some places it has values 1, meaning those specific features, chemical features that are present in a specific compound are uh, given value 1. If the feature is absent, they are given value 0. So for all 1128 compounds, we calculated embeddings and we calculated fingerprints. Okay, so now the next step is very straightforward if you are familiar with sort of traditional machine learning model development approaches. So for this example, we'll be developing a support vector regression model. So what it does is it basically takes the data from the training data set. It tries to sort of uh, project the data in hyper parameter space and try to find a separation uh, between the positives and negatives in the training data, right? So there are different ways. You can use linear regression, you can use random forest. In this particular example, we are using support vector regression. If you are interested more in learning about the method and the parameter that it takes, you can follow this link here. Okay, so uh, in the beginning, we will split the data into test and training. So basically, we are sort of in this particular cell, we are using chemical fingerprints or Morgan fingerprints that we generated for training the model. So this whole cell will focus on using fingerprint for developing a support vector regression model. So basically, we are specifying what are the uh, input feature columns. So here, those columns will come from fingerprint, and uh, the 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 column is converted into a list by adding these additional functionalities at the end. So we are taking the fingerprint column and converting into a list of 1024 vector length values, either 0 or 1. And we are specifying the target column as y. So this column will contain the ESOL values for those compounds. And in this step, we are splitting the data set into test and training. So basically, we are uh, taking 70% of data into training set and remaining 30% in the test set. So in this line, so once we have splitted the data into test and training, we are instantiating a support vector regression model with these parameters. So basically, what type of kernel? So here we are using radial basis function, different other parameters. You can check those parameters in detail here in the link, and you can tweak those parameters and see whether it improves the model performance later on during the exercise. Okay, so we are instantiating a support vector regression model, and then we are asking this data to be fitted in SVR model. So we are using the training data, and then we are, once the training is performed, we are using the test data to predict the labels. So basically, the ESOL values for the compounds in the test set, right? Once we obtain the predicted values, we are comparing those predictions with the ground truth. So basically, what are the actual values that are experimentally calculated, measured, and comparing it with the predictions. So we are comparing those predictions, and we are obtaining basically two matrices. One is mean square error, and one is R square. So mean square error meaning how far those predictions are. So how those predictions deviate uh, from the actual values, and taking uh, the mean value of those errors, and R square values. So meaning how well they correlate with the predictions, the actual values. So let's execute this cell and see what we obtain for mean square error and R square values. Okay, so for the mean square error, we have 1.37, so meaning for these y values,